This is AP Calculus BC, and in this video, I'm going to talk about the logistic differential equation. So first thing you might notice here is that there is not a section number attached to this topic, and that is because your book doesn't really have this topic covered in a lot of detail. There's a brief mention of it, I believe it's section 8.3, but really your best resource for everything you need to know about logistic differential equations is going to be this set of notes that you have here. So the logistic differential equation is primarily used in situations where we're talking about population growth. And if you remember, we looked at population growth back in section 8.2, and we talked about exponential growth, and we used a really basic population growth model. So when we looked at that, what we would be assuming is that population would grow exponentially, essentially forever. And that's not really very realistic. So over the short term, yes, we can use a population growth model that's purely exponential. But the reality is we really get more of a logistic growth curve when we're talking about population growth. And the logistic growth curve just takes into account things that would prevent a population from growing infinitely. Like, for example, just resources, the amount of space that you have. There are a lot of things that will happen if a population starts to get too large. Certain types of animals can get overpopulated in an area. Sometimes a disease will start spreading within that population, or things will happen that will prevent that population from growing. So that's really what we're looking at here is this idea of logistic growth. So the differential equation that we use for this is a little bit different than the differential equation we use for simple population growth. So you can see here, this is the logistic differential equation. So we still have the first part of it is exactly the same, k times p, but now that's multiplied by 1 minus p divided by k. And notice we have a lowercase k and a capital K. So the lowercase k is still our proportionality constant, but the capital K is referring to the carrying capacity. And that is what we call really the equilibrium population that could be sustained forever. So that's really what, when we think about population growth, that's sort of what population growth is always going to want to approach. It's going to want to approach that equilibrium value, which we refer to as the carrying capacity. Okay, so now looking at this differential equation, it says, what if population is small? So take a look at this differential equation. And if the population was very small in relation to the carrying capacity, that would essentially be 0, and we would just have a population growth of k times p. But as the population gets larger and larger, you can see how the value that we're multiplying to k times p is going to get smaller and smaller and smaller, because as population starts to approach carrying capacity, we're essentially going to get a value that's closer and closer to 1. So if we were exactly at the carrying capacity, our rate of growth of our population would be 0. Okay, so that would mean we had reached the equilibrium point. Okay, so here is an example of what that logistic curve looks like. Now, they used L here for the carrying capacity instead of K, but it's still the same idea, this general shape. You can see at the beginning of the curve, we were growing what looks like exponentially, and then somewhere in the middle here, our growth rate starts to flatten out, and you can see that we go from a graph that's concave up to concave down, and then we start to approach that carrying capacity, which is L in this graph. Okay, so that's really what we're looking at. So early on in the process, we do have exponential growth. As time goes on and the population continues to grow, clearly our population growth is going to decline. Okay, so now when we look at logistic differential equations and we solve these, this is actually a differential equation that you're probably not going to want to solve out every time you see one of these, and I'll show you why in a second. They're pretty difficult to work with from an algebraic standpoint and just from a calculus standpoint in terms of the integrals that you have to solve. But in terms of understanding how this works, we do have the same kind of setup. We have a slope field here, and you can see in the slope field that we've got different shapes for our solution curves depending on our initial population. So for example, if I had an initial population of 200, you can kind of trace through and you can see how we kind of have that logistic growth curve shape that is sort of the standard logistic growth that you would typically think of. Now, notice here, if I start at a higher population, let's say my population starts at 800. Well, now I just have a graph that's concave down the whole way. No matter what happens, though, I have this horizontal asymptote that is my carrying capacity. Let's say artificially somehow we make the population too large. Like, for example, if we were looking at the wolf population in an area and we just took a bunch of wolves and put them into a certain space and there were too many, then what would happen is our population would very quickly decrease to that carrying capacity. So we do have some different shaped solution curves depending on our initial population. Okay, so let's take a look at actually solving one of these. Now, I'm not going to go through all of this in detail. You can look at this on your own. The main idea is we can do separation of variables and solve out a logistic differential equation. However, as you will see here, you definitely don't want to do that. I've got all the steps here. You can kind of see how I separated the variables. This involves using partial fractions. It gets pretty messy, but you can see all the steps, and I would encourage you to review those steps. But I'm never going to ask you to solve one of these logistic differential equations. The main purpose here is, in the end, I do get a solution curve, just like we would before. We have this arbitrary constant A, and then using our initial population, we can solve for that value, and now we have population in terms of time. Okay, so not incredibly difficult to do. I mean, it's the same general concept. It's just that, algebraically, it's a little bit of a mess. Okay, so in general, we know what our solution is going to look like. If we have a differential equation that's in this form, Kp times 1 minus P over K, then we know our solution is going to show up in that general form. Carrying capacity over 1 plus A e to the negative kt power, where A, that general constant A, is going to be the carrying capacity minus the initial population divided by the initial population. And if you work through that example problem that I had there, you'll see how that A value comes into play. Okay, so the idea is you don't want to solve one of these differential equations every time you see it because it's too much work. You saw in the steps that I showed there, that was probably a full page of work, and I even skipped some of the algebra in there to make that a little more concise. So really what we want to do is we want to be able to recognize when we have a differential equation that's in the form of a logistic differential equation, and then we just want to know, okay, if my differential equation's in this form, this is what my solution curve is going to look like. So that's really how I want you to approach these. It's just a specialized form of a separable differential equation. Okay, so let's take a look at a few examples here on how these would work. And I want to mainly show you that, I'm not expecting you to work through a bunch of steps here. If you can remember what the general form of the differential equation is and what the general form of the solution is, these are actually fairly simple problems, even though it seems a little bit intimidating at first. So on this problem, it says the growth rate of a population of bears in a newly established wildlife preserve is modeled by the differential equation 0.08 p times 100 minus p. And on part A, it says, what's the carrying capacity? B says, what's the bear population when the population is growing the fastest? And C, it says, what is the rate of change of the population when it's growing the fastest? Okay, so first of all, this is not in the form of a logistic differential equation, or at least not the standard form right now. So in order to have the standard form, I need this value to be a 1. So I'm going to factor out a 100 to get this into the correct form. So dp dt, when I factor out at 100, this is going to become 0.8p times 1 minus p over 100. Okay, now I have it in that standard logistic differential equation form. So from that, I can see the carrying capacity is 100. I can see my proportionality constant is 0.8. And now I can answer these questions. So part A, what is the carrying capacity? Well, the carrying capacity pretty clearly here is equal to 100 based on the form of that differential equation. And part B, it says, what is the bear population when the population is growing the fastest? Okay, that is one thing we haven't talked about yet. Let's go back to this graph that we had of this logistic differential equation. Where we are going to have the steepest slope. So think about the shape of a graph here. It starts out, if I start below my, below the halfway point on my, from the carrying capacity. If If I start out down here, for example, at the beginning of this graph, it looks concave up. And then at some point in the middle, it switches to concave down. And it turns out that at half of my carrying capacity, I switch from concave up to concave down. So I could go through and I could look at finding the maximum value of dp/dt by using derivatives. However, just as a general rule, when we get to that halfway point between a zero population and the carrying capacity, that's where we're going to have our fastest rate of growth. And then from that point on, growth rate is going to decrease. So for that question, back where we were, what is the bare population when the population is growing the fastest? That's going to occur at the point when population is equal to 50. And remember, that just means that dp/dt is at a maximum value when population is equal to 1/2 of my carrying capacity. Okay, so keep that in mind. That's just a general rule that we can follow. Okay, part C, what is the rate of change of the population when it's growing the fastest? So now that we know how to read all of this, all I'm really doing here is I'm essentially saying, okay, what is the rate of change of my population? It's dp/dt. What's that value when population is equal to 50? Okay, so I know the equation for dp/dt. I've got an equation of 0.8 times my population times 1 minus my population over 100. And from there, we can just plug that into the calculator. It turns out that rate of change would be 20 bears per year. Okay, so fairly easy to do once you know the key things to look at on these types of questions. Okay, so let's move on down here and look at one more example. So this is actually an old AP test question. So this is a topic that will show up on your AP exam. Typically, these questions are pretty easy to deal with. So it says, suppose P of t denotes the size of an animal population at time t, and its growth is described by this differential equation, 0.002p times 1,000 minus p. The population is growing the fastest when? Okay, so why don't you just pause the video. When you come back, I'll show you the solution. Okay, so for your solution here, this is a lot like the one we just looked at, right? We don't have the differential equation in the correct form. Based on the fact that we're talking about population growth, though, and I can see that this isn't simple exponential growth, I'm going to assume that this is a logistic differential equation. So I'm just going to get dp/dt, because really what I need here is the carrying capacity. Factoring out 1,000 here, I'm going to get 2 times p times 1 minus p over 1,000. And now it's pretty clear that the carrying capacity is 1,000. So my population is going to be growing the fastest when I'm at half of the carrying capacity. So the answer there would be B. Okay, when you work through these problems, that's really my expectation for your understanding of this. I want you to know the standard form for the differential equation. I want you to know the standard form for the solution to the differential equation. And then I want you to understand what the carrying capacity is and understand how that relates to the rate of growth from the standpoint of when we get to half of the carrying capacity, we have our maximum growth rate. Okay, now I don't have an assignment for you in Wiley Plus on this. What I do have is a worksheet here. I'm not asking you to do this entire worksheet, and I'm not going to make you turn in this worksheet. What I am asking you to do is work through some of these problems so you feel like you have a good understanding of how this works. So they're fairly simple. Once you understand all of those basics that I mentioned, you can work through these problems very quickly. So I've got some that are kind of repetitive here at the beginning, but when you get to number 3 and 4, those are actual multiple choice that are old AP multiple choice questions on logistic differential equations. So make sure you try those. And I would say do 1 or 2 of the other ones to where you feel fairly confident about how everything works, and you should be good to go. Now, I did give all the answers here so that you can check them. And you can let me know if you have questions on it. But I think for the most part, you will find this to be very, very easy as you work through this assignment.